This is ES110. We're going to work on class 5 today. It's kind of covered up with me. Right there it is. Class 5. We're dealing with section 2.5 in chapter 2. This is the last section. Now, we've just recently done 3D vectors, and we were finding the resultant with them. Now we want to try to find the equilibrium. All right, we're going to use equilibrium, the sum of the forces, in the same way, in a similar treatment, right? But now everything is in 3 dimensions, whereas I think in a previous section, we did 2 dimensions, right? Is that true? Yes, I think so. So basically, there's not that much in terms of the chapter content that we need to look into. Let's take a look at sample problem 2.9. It's a pretty long problem, especially the way that I'm going to draw it out here. I'm going to introduce using just a slightly different variation of what you've seen before when it comes to doing the vectors. I'm going to use the position vector. Now, instead of those little distances, dx, dy, dz, we're going to use r, and then we're going to come up with a nomenclature for the thing. And that nomenclature is going to be, I'm not sure if we've done this yet. A position vector, let me write this out here. A position vector is going to be something like RB with respect to A. That's like an example, right? Well, what we're going to say right there is a position vector is going to be equal to the position of B minus the position of A in the I direction, the position of Y minus the position of A in the J direction, and the ZB minus ZA in the K direction. So what we're doing is we're using A as the reference, and we're finding the location of B. So this is referred to as B with respect to A. I don't know if I can't recall if I've introduced that before, but that's the main way that we're going to arrange to find the location of something, right? So when we go to write out what each of the vectors are for something, like we want to try to get the magnitude of this force right here, we're going to lay out this position vector right in there. Okay, so this first one right here, we want to draw, when we're doing equilibrium, we always want to use free body diagrams. So let me read out the problem first of sample 2.9. A 200 kilogram, right here, 200 kilogram cylinder is hung by means of 2 cables, A and B, AB and AC, that are attached to the top of a vertical wall, so like right here, and horizontal force, this is is being pulled, it's perpendicular to the wall, and it holds the cylinder in the position that's shown. Determine the magnitude of P and the tension in each of the cables in order to achieve this right here. Now, don't quote me as saying this because I'm a big fan of the free body diagram, but this problem almost doesn't need the free body diagram. We're going to kind of use through the vector treatment of the thing, but the free body diagram does help us think. And a lot of times for the 3-dimensional one, what you'll see is they will kind of cop out. It's not much of a free body diagram right here, right? Well, we're just going to see this little particle right here, and we'll put in this force that we'll call P, and we're going to call up a force this way and a force that way. I prefer to do free body diagrams in 3 different views as opposed to doing the 3-dimensional ones. So that's why I'm calling it like sort of a cop-out. But we're going to call this F AC, it's acting right there, and F AB, acting right there, right? We also are. I forgot. We also have to put in the weight, and we'll put that down as a vector right in here. And we might even we want to put that guy as a vector hat right in here. I kind of want over to the side. Maybe I'll write down on another piece of paper. I would show you that in this problem, I think it makes more sense to define. This is the x direction. We need to do that anyway. This is the y direction, and this is the z direction. All right. So we've established where that is, and I think what we need to do is part of this. Did we say where 0 was? Be careful with that. I think we established. Let's make z like right there. That's a good spot for z to be, right? Because it's in line with this a. So we'll put a at the 0 of y, right? So a is located at where y is equal to 0, right there. But I think that I would probably want to have made this FBD just because of the arrangement of the thing, kind of from the side right here, right? And declared that this was in the XY plane, that we were looking right there, and that I was looking at this and here, and then I'd also maybe write out, side by side with each other. This would be my method of doing the thing, that they were like one on top of each other, like superimposed, that you could barely see them happening right there. But because they're not going to be equal to each other, this wouldn't be the greatest view to use. But to me, that's what a free body diagram will generally look like. So this might be the exception where we're just working out right here. I'm saying this because this is more of a methodical approach that will help you a lot of times. When I'm referring to a free body diagram, we want to do it in one plane. But this is still equally valid. It's just that I want to show you where the more typical situation, in my opinion, would be. So anyway, we've drawn this thing out, and it just not is all that thrilling when you put it out there. But our mission here is to find this. So we write out the sum of the forces equals 0 right here, and that's generic because that's the vector right there. So if we were going to write out that equation, we would say that AB plus AC, and it depends how we write this thing out. Yes, let's just write this. We're not giving this thing any signs by way of this vector right here, right there, right? That's what we're saying. We say this plus this plus this plus plus must equal equilibrium. Must be equal 0 for equilibrium to take place. Now we can start off with some preliminary things that we know happen right here. First off, we can know the direction of P. So that's going to actually be P times I right there, right? We know that it's this is the magnitude of P. This is the P vector. We could say the W vector, the weight of this thing, is going to be equal to a negative mass gravity J right there. And we can even put in some numbers there. Here's the negative to there, 200, 9.81 J, and that's going to equal a negative 1,962 J newtons. So it's downwards, right? So we've gotten that vector out of the way. So now we need the position vectors to define, and we'll also introduce. It was already introduced, but we'll use the lambda designation for this, for the direction cosines, if you will. That's a phrase we'll use. Call that lambda, the direction cosines. So first off, this cable tension, the way that it's drawing is going to be A with respect to B. B with respect to A. B with respect to A, or B with respect to A, will give us a direction cosine that's going towards B, right? So direction cosine of B with respect to A And if we needed to, we could walk through and say the things of like this xb minus xa and that kind of this. But we could kind of observe it from here, that in the x direction, b is in the negative 1.2, right? So negative 1.2 I plus, and it's going upwards. I'll go 2 meters right here, okay? And so it was 12 meters all the way to the top, 2 meters from here, so it's going upwards, so it's positive 10. For the z direction, it is going in the positive z direction, so it's starting at A, going to be 8 meters over. Right next to it, I decided to... I'm going to have to go to multiple pages right here, so I'm going to go ahead and just write it underneath there and stop trying to conserve paper here. That's also a good advice to you, is to kind of let go of the desire to use as little paper in your career as possible. It's only going to slow you down and make you get frustrated as you have to cram stuff in. And I think anything that kind of slows you down here is worth not doing. Not to be constrained by things that are unnecessary. 12.86 meters, right? So if you're going to have something, we would say that we have a lambda AB. We could even call it lambda A with respect to B, which is actually going to be a vector right here. And we'll take a negative 1.2, divide it by 12.86. And if we took the inverse cosine of that, we would get that theta x, by the way. Same thing here. We're going to the 10, divided by 12.86, J, and then take 8, divided by 12.86, K. Work all those out here, and we get a negative 0.09331 I plus a 0.7775. There's 3 sevens in there. 0.7775 J, and then a 0.6220 K. And you notice that all these are less than 1, and if you were taking the sum of the squares, the square root of the sum of the squares of these, you would see they would equal 1. Because this is, in effect, sort of like a unit vector kind of thing. It's a direction cosine. It establishes the orientation of the vector without a magnitude. So just recognize that when we want to have the vector AC, we take a magnitude FAC and multiply it by this direction cosine, and that right there will give us that full vector, that force vector right here with the magnitude and direction. So this serves as the direction part of it right there. I just wrote the wrong thing. Sorry, that was supposed to be B, AB. I skipped down a line on my page. Just know that that's going to be true right there. Now for the other vector right here, really slow going right here. I'm getting tired already of recording these videos. I want to go AC. So a lot of things are going to be the same. I'm going to take the C with respect to a position vector. And I think in the x direction we got the same thing, negative 1.2. I hope I didn't mess that up right there. No, I think I did okay. There's a line that I could be looking at the wrong numbers of things. So I think I got it. It's also going to be up 10, right? So it's also going up the same amount. It was starting here at 2 right here. I think the only thing that's going to be different is the z. The z is now going to be in the negative 10 k direction, right? So let's slide that down here. You can see that it's going in the negative z direction, in that direction right in there. And that k is looking pretty sad. Can I fit him next to it? Boy, I really can't. Okay, so I'll cram him down here. No, I'm going to fit it next to it. CA, the absolute value right there, is going to be the square root of negative 1.2 squared, 10 squared plus negative 10 squared. And so we're going to get 14.19 meters. So a lambda, we'll call it AC. I almost want to call it like C with respect to A is probably more accurate, right? I'm going to say I could call that B with respect to A, and that could be C with respect to A. I'm going to see if the book does that or not. I kind of want to. Okay, so we have negative 1.2 divided by 14.19 I, and a 10 divided by 14.19 J, and a negative 10, 14.19 K, and we will end up with negative 0.08455 I plus 0.7046 J plus negative 0.7046 K, right? And then if we were going to say the force at AC would be that magnitude of that force times that lambda AC as we've written it right there. We'll take a peek at the book when we're done with this. So we want to come back up to this equation right here and fill him in right there, right? So we can fill that in with the things that we have. We have this guy, this guy, this, and this, right? So we're going to stick that back into that equation. So let's start out with a FAB, right? So let me rewrite this equation down here because I don't want to think. So I am rewriting out so I'll take that FAB, and that's going to be this FAB, right? Magnitude times each of these things right here. So I'll write them out in big terms. Okay, no, actually what I'm going to do is I'm going to take, so this is, it would have been unnecessary to write out the whole thing long ways and then to pick and merge it too. Let's just go for all the i's, right? So we're going to take this equation and look for I. I like to write it out. No, I'm going to go, sorry. Change my mind. Let's take the I of this, FAB, times negative, right here, so it's a negative 0.09331. Let's take the I of this, so we're adding in the I, it's FAC, and the I is a negative 0.08455, right? And then take the I of this, which is nothing, right? There's no I involved in W, in the weight. Remember, the weight is only in the J direction. And then we take the I of P, which is completely in the I direction, right? So all we're going to have is a plus P. And that's all in the I. Now let's add up the J. So we continue doing the same thing. We take this FAB in the J direction. So that's going to be FAB times our where'd you go? 0.7775. and it's positive. Now take the J of the AC, and that's going to be plus FAC times 0.7046, right there, right? And now we take the J of the W, and that, as you'll recall, is completely negative 1,962. So minus 1,962, and that's all that she wrote there, right? And now we continue with this and do it in the K direction, right? So I have to come back down to another line right here. And what I do in the K direction is I write FAB in the K direction, which is right there. So I'll move this guy up a little bit. It's going to be 0.6220, right? And now I take the AC in the K direction. So plus FAC, but that's going to be a negative 0.7046. And anything in the K? No. Anything in the K? No. So that right there is all there is to K, and it all has to equal 0. And the only way that this could be true is if this is equal to 0, that's equal to 0, and that's equal to 0. Now you might have already recognized what we're going to, what the secret to the solution of this. These are really 3 equations right there. Each of these equals to 0. But instead of so there's like 3 equations and 3 unknowns: P, FAC, FAB. We don't know the tension in either of these, and we don't know what this force is. But so we can have 3 equations, 3 unknowns. But this one right here kind of like gives us a sort of a little bit of a helper, right? We could set this one in terms of FAB, in terms of FAC, or vice versa, and we could plug it back into this one with a number, and we can find what the value is, right? So we go ahead and do that. And so for in the K direction, I write this right here. I don't know why I gave that umlauts. I give a hat. In the K direction, we can write out FAB is equal to 0.7046 divided by 0.6220 FAC, right? I can call that equation 1. And then in the J direction, I can go ahead and, I'm sorry, I like to do this. This is my preferred way of writing the thing out, and I didn't do it. 1.133 FAC, right? And that was equation 1. I'm going to plug this back in for AB right in there. So what we will find, we'll get 1.133 times our 0.7775 FAC, and then we still have our, I guess I put them in front, 0.7046 FAC, and then minus 1,962 equal to 0. So I'm able to find FAC, and that's going to be 1,238 newtons. And I plug back into 1, right? And I find that FAB is going to be 1,402 newtons. So now I found the tension in each of these. So now I come back up to I right here, this equation for I. Plug it in, you can find P. So that's going to be our I. And plugging that in, 1,402 times our negative 0.09331 plus our 1,238 times our, where'd you go up here? Negative 0.08455, and then plus p, right? These are negative and negative, and positive, so we can find what p is going to be is 235.5 newtons. Like that, right? So the answers are magnitude of this 236 newtons, magnitude of this right here 1,402 newtons, and then the magnitude of AC is 1,238 newtons. Now, the fine people of McGraw Hill just gave me finally the 12th edition of the combined one. That's a big book, man. That's a good bargain, though. Let's see. Let's check this thing out. This is sample problem 2.9. So let's get the most out of our money on our book for our book things. And let's see. We're sample problem 2.9. Excellent. Boom. So we're checking this puppy out. You can see what they decided to do. I don't know if I really like that that look here, but the same thing that we did it here and here. This is what they're calling their free body diagram. It's but you can see we have their lambdas AB and lambda AC. They've arranged right in here. I don't know what all that stuff is. But here they decided to use capital T. I don't like using capital T, but that's me. Here's your vectors, and they're adding the things up. They did all their positioning vector things right up here. So here's their position vector. They didn't decide not to do that subscript thing that for the thing where they're going from A to B. This is their convention for the thing. I think you're better off with an R, B with respect to A, because that's what we use in dynamics, which is later on in this same book right in there. So I want to be consistent. Might as well use it now onto things. And so anyway, they draw the thing out, and you can see here's this long equation that they've placed into here, and they show it separated out into separates, and then they show the thing right here. So I think did I pick up another problem? And yeah, so I think that's the only sample problem in this section 2.5. I think I created another video for this, or I asked you guys to do one in class. We'll see what the next one is. Hopefully this video might help someone who is reading the book and having a hard time understanding how to approach that sample problem. So thank you and good luck. Good night. 28-minute video.